Hi, my name is Tom and you are at level 17 out of 30 easy steps to learn everything about Einstein's special relativity. So far we have been celebrating and doing great discoveries. But now it turns out that there is an issue with our new discoveries. A major crisis is coming up. It's called MMX. And I did not tell you yet what MMX is, but we will learn soon. And this is the first level out of all 30 levels where I will not give answers. I will only raise questions. Deep questions, important questions, questions that push the boundaries of physics and made all the greatest minds in history trying to solve this. So, you want to know what the crisis is? Here we go. GP, hit it! We have reasons to celebrate. Why? In level number 1, I asked you to join me to climb Einstein's mountain. And I said we can do it 3 ways. We can do rock climbing, we can try popular science, or we can choose something in between these two extremes. Walk the mountain. Take 30 steps to get to the top. And we've done a lot, right? In level number 2, the basics of algebra. Vector fields, very important. Calculus, calculus, yes, we had to do calculus. We learned about Coulomb's law, the electrostatic force. Then I think the most difficult level of all, number 7, we learned about divergence and curl inside vector fields and the dot and the cross product. We met Gauss and his law on electric flux, and he could see through the walls. Ørsted, who saw the needle of a compass moving in the vicinity of an electric wire. We talked about Faraday and his law of induction, where electricity and magnetism meet. And then we had level 11, Maxwell's equation, which was a full marriage of electricity and magnetism. And I told you, you can relax now and join the view. This is base camp number 1 on our mountain. And then we moved to other things. We talked about waves in general. Waves through ropes, waves in the water, etc. We talked about Doppler, the effect, and we did some exercises with our brain to switch perspectives back and forth, different things, and try to see if we can tell the velocity from different views, different point of views. And I told you, Einstein's theory on special relativity is nothing more than changing perspective. So that was a really important exercise in level number 13. We did the super level at level number 14. Inside the Maxwell equations there was a secret, and we discovered electromagnetic waves. Then we moved on to a different topic again, the speed of light and its history. And in level number 16 we did the double slit experiment of Thomas Young, and we found out light is an electromagnetic wave, and all electromagnetic waves travel at a constant speed through vacuum of around 300,000 kilometers per second. Celebrations. Celebrate the electromagnetic wave. Celebrate the discovery that light is an electromagnetic wave. But after celebration comes headache, sometimes, depending on your consumption of alcohol. Houston, we have a problem. If light is a wave, what is its medium? If we have a rope, in the gym, and the wave goes through the rope, when we move the rope up and down, the rope is the medium. When we go to the sea, on the beach, we see that the waves travel through the water. Water is the medium. When we listen to sound, sound is being propagated through the air, little vibrations that reach our ear and tell our brain that there's noise, that there's audio, that there's sound. There, the air is the medium. What about light? And if there is a medium, like water, what is its relative speed to Earth? Because we see light travel throughout the universe. So it has to be everywhere, this medium. And just as we saw that if a water wave moves through the water, it has a velocity with respect to the water. It's relative. Velocity is not an absolute, it's a relative. So it's how fast is the water wave traveling compared relative to the water itself. And this medium of light, is it just fixed in the universe while all the planets and stars are moving through this medium? Yes or no? Or is it moving? Is it being affected, this medium? Like is the water being dragged while the water wave is going through the water? Completely in matter or partially? Those are really big questions. What about Doppler? Does this also hold up for light? And, well, what about Maxwell equations, and where is the medium there? And Galilean relativity. We did Galilean relativity a few times, but in the first few levels we did it. And, basically it says, if I'm traveling towards you at 30 meters per second, you could argue that I'm not moving at all, but you are traveling to me with 30 meters per second. We can switch perspectives. I could say, I'm not moving, you are moving. But you can say, no, Tom, I'm not moving, you are moving. So how does this work with light? And what about Newton, when he talked about the particle theory, etc. Is relativity still true, yes or no? Big questions, because light turned out to be a wave. So let's zoom in on the medium of light. Here we have the different, one back. So we talked about waves in the water, which are transversal. The water is going up and down, but the wave is going from left to right. So the velocity of the wave is perpendicular to the oscillation. And that's what we call a transversal wave, a T wave. And sound, where the vibrations move in the same direction as the wave, is called a longitudinal wave. But every time there is a medium through which the wave propagates. So there has to be a medium for light. There just has to be, because it's a wave. Well, sound, for instance, stops when it hits vacuum. So you can't hear anything in the universe. So when you're watching your favorite science fiction movies and you hear the explosions, that can't be right. You can't hear explosions in the universe because there's a vacuum, and sound needs air. It needs a medium. So if the air is not there in the vacuum, then the sound can't travel. No sound in the universe. So light. Well, light travels through vacuum. So whatever the medium is, it's in vacuum as well. But what is it? They gave it a name. The luminiferous aether. You have to call it a name, so that's what they called it. And, well, I talked about Newton, and his particle theory in optics, but for his theory to work, even Newton needed some kind of a medium, some kind of ether through which the particles fly. We did Young in the previous level, the double slit experiment, and then we knew definitely it's a wave. And Fresnel said it was a transversal wave, right? And to make that work, you have to ether. So everyone agrees on one thing: we need the medium of light. There must be ether. And if it's there, then it's relative, right? The velocity of the waves going through the ether is relative to its medium, like the water waves relative to the water, the rope relative to the rope, etc., etc. So if you change perspective, the observed, the perceived velocity of waves changes. If I run towards the wave, it seems it's coming at me faster. If I run away from the wave, it seems it's slowing down, right? But how does this work with light? And they thought about, well, maybe whenever light goes through something, its medium also goes through that something and it drags with the something. So if we have a bucket of water and the light goes through the water, the ether, whatever it is that air that light needs, is also in the water and it moves with the water. It drags it, because otherwise it just makes no sense. So then this question is really nice. When we talked about the sound, the speed of sound, I told you that the denser the medium, the faster the sound wave goes. In air, it's around 300 meters per second. But then I told you if you have a diamond, sound will propagate through a diamond 12 kilometers each second. Because a diamond is so dense and air is very loose, Even water, it's over 1 kilometer per second in the water, because water is way dense than air. So the denser the medium, the faster the wave goes. Light goes incredibly fast, 300,000 kilometers a second. So the medium of air needs to be really dense, denser than diamond. But still, I can just move my hand and it's not being stopped by whatever the medium of light is. Planets just move through the ether. This is really weird. Huygens, we met him. It has to be a longitudinal wave. He was wrong about the longitudinal part, but he was right about the wave part. And, well, waves need mediums. And then in 1810, Arago, I don't know how to pronounce it, he tried to demonstrate ether, but he failed. Fresnel said, well, he came up with a new theory. Maybe whatever it is that light needs to propagate is partially dragged in matter. And that would explain why the experiments of Arago failed. If you just assume not full drag but partial drag, we can explain his results. Okay, new theory, partial dragging of whatever it is. But then Stokes came along and he said, no. It's either fully dragged or not at all. And then Fizeau came along and he measured the speeds of light in moving water. And so he did it. He moved the water and to see if light goes faster or slower when the water moves. And if that was the case, then maybe the water drags the medium of light with it, either fully or partially. And he said, well, Arago and Fresnel with their partial dragging, they are right. And Stokes, who said it has to be completely dragged, he's wrong. That's what his experiment showed him. Then Lorentz also said, full drag is wrong, partial drag is right. But we still don't know what it is, right? And then we had Michelson and Morley, and they repeated the experiment of Fizeau, and yes, partial drag. So at that time, it seems like there is something called luminous ether, ether for light, and it's partially dragged. So that would solve all observations in physics. But in 1887, Michelson and Morley did the famous experiment, and it's so famous it has its own acronym, MMX. The M for Michelson, the M for Morley, and the X for experiment. And they were really eager to demonstrate ether. And just as you can show in the water, if you swim to the waves come at you faster. If you swim away, it's slower. And that's what they wanted to do with light. It failed. no matter what they did, the speed of light was always the same. Which makes no sense, because it's a wave, and if I run to the wave, or if I run away from the wave, it should have an effect on the perceived velocity of the wave, and from my point of view. I mean, we have known this, from Galileo Galilei. It's Galilean relativity, It's if I move to the wall, the wall moves to me. And if we don't move, nothing is moving towards each other. And now it seems that no matter if I move to the wall, or if I move away from the wall, or I'm not moving, the velocity of the wall is always the same, the velocity of light in this case. And everyone thought, well, there has to be something wrong with the experiment, because there has to be ether and there has to be relative motion. But they can't. They said, well, unless it's completely dragged, that could explain it. But then Stokes would be right, and Fizeau and Fresnel and Argo would be wrong. So there is multiple experiments and they are not in agreement with each other. Major crisis. And sometimes a crisis is the best thing that can happen to you in physics, because now the greatest minds in the universe on the planet Earth had to come up with solutions. Fast forward to today, the completely dragged model also is not correct. And the partially dragged model is also not correct. So maybe the whole idea of ether, of light needing a medium to pass through, to propagate through, maybe that idea is wrong. But it can't be, because it's a wave, and a wave needs a medium. That makes perfect sense. Relativity. I think I spoiled it already. It gets nasty. Well, we know about relativity, right? So again, I'm moving towards you, you're moving towards me, I'm running away from you. The velocity between you and me changes when we start taking different velocities. What we do know in physics is that accelerations, so the change of velocity, the change of speed, is the same for all observers. No matter if I run to the experiment or run away from the experiment, the change of velocity is the same for all of us. I mean, that's a safe haven for physicists. So Newton, which was all about accelerations, it's not on Einstein's mountain. Maybe I'll do another mountain on Newton. But in all inertial frame of references, you have to remember what that was. A frame of reference moving at a constant velocity in a straight line. Different frames of references moving with different constant speeds. No matter in which frame you are doing your experiments, the accelerations or the laws of physics will be the same. But that's not for speed. So speed is something else. Speed is relative in the universe. There is no something called as the speed, the velocity. It's a vector, it has a strength and a direction, and it's always relative. It's always the speed compared to something else. Always. So, but Newton, well, in his equations, F equals mass times acceleration, has no velocity in there. And well, that equation made us just build a machine, jump into it and fly to the moon and walk on the moon. So great for Newton. But if we look at the electromagnetic waves, there was a velocity in there. So we have a physical law containing a velocity. But we know that physical laws will be the same in every inertial frame of reference. They are not affected by the velocity of the observer. But electromagnetic waves have a velocity in them. And of course, if I run to the electromagnetic wave, it appears to come at me faster. And if I run away, it comes at me slower. But all the experiments tell us, no, that's not the case. It's always the same. Crisis. crises. Crises. I mean, I've told you all this, you know, and we can test it, you know. We've done millions of tests showing that the velocity of electromagnetic waves and light specifically does change when you look at it from different point of views, but it doesn't. It's always the same. It really makes your head ache. So, physics is brutal. Here we have a wave which does not behave as all the other waves. It doesn't seem to need a medium. And it's always the same. It just violates everything that we have known about relativity. So, summary, they did this experiment. We can't demonstrate the existence of ether. Whatever we do, the speed of light seems to be the same. We are disagreeing on whether is an ether, and if there is it fully dragged or partially dragged. And whatever we do in testing, we can't demonstrate the existence of ether. So, and, we know Galilean relativity, again, running towards you running towards me. The velocity of two people relative to each other affects our observations. So Galileo has to be right, you know. We are not going to say that Galileo was wrong. Sometimes we do, right? We come back at fundamental concepts in physics and we change them, adapt them, correct them. But in this case, Galileo is just right. You know, we know he's right. Everyone knows he's right. Newton. Well, Newton is Newton. When Newton talks, you listen. So, questioning Newton, that's a no-go. And questioning Maxwell, well, you can question Maxwell, but Maxwell's equations gave us radios, cell phones, Wi-Fi, and everything else. And that works. It's real. So, you know, maybe this is a disappointing level for you all, but you have to understand the discovery of electromagnetic waves, and that light is an electromagnetic wave, was a reason to celebrate. But then we found out that electromagnetic waves do not behave as other waves. And that was a crisis. That was a problem. So we need a fix. And we need it fast. I think this is it, right? Yeah. I want to thank you. I want you not to go to the next level today. Go to sleep. Think about it. Dream about it. And feel the same as all scientists felt in those days. Crisis feeling. They had no idea what to do next. And what happens when you have no idea what to do next? You get creative. Yes. And from the next level onwards, we will get very creative. Thank you for watching, and I hope to see you next time. GP, hit it!